second half of section 1.1, page 18, piecewise-defined functions. All right, remember that a piecewise-defined function is exactly what it sounds like. It's a function that's being defined in pieces. So here's what example 7 says. For f of x, if your x value is less than or equal to 1, then we want you to use this piece of the function, 1 minus x. But if your x value is greater than 1, we want you to use this piece of the function, x squared. So when they give me a value like f of 0, remember that's our function notation that tells me to put 0 in the place of x. So if I came over here and put 0 in the place of x, I'm not going to plug 0 into both of those pieces. I'm only going to plug it into the piece that is appropriate. So I have to determine, is 0 less than or equal to 1 or greater than 1? Well, of course, it's less than or equal to 1, so that lets me know I should use the top piece of that function, 1 minus x. So I'm going to plug 0 into the top piece of the function, 1 minus x, put 0, of course, in the place of x, and we would get 1. All right, how about f of 1? Am I going to plug into the top piece or the bottom piece? All right, so it said if x is equal to 1 to use 1 minus x. So I'll plug 1 in the place of x, and I'll get 0. How about f of 2? Am I using the top piece or the bottom piece? Bottom piece, because 2 is greater than 1, so I should use x squared. So if I put 2 in the place of x, I'll get 2 squared, or 4. Now, to graph a piecewise defined function, I could be here all day making a table values. So that's actually a better way of going about doing the graphing, and that's to actually graph both of the functions and then just keep the pieces that you need. So, for instance, for the first one, they said we want the graph of 1 minus x. So I literally would graph 1 minus x. You can graph that line however you want to. I did a y-intercept of 1 and a slope of -1, so rise -1, run +1. So there's the graph of my line. And then I'm only going to keep the piece of that line where x is less than or equal to 1. Now remember, we're looking at the x values, not the y values. So if I look at this horizontal axis, right here is where x is equal to 1, so close dot right there. And then all the values less than 1 would be to the left. So I'm going to keep that left-hand part of the line, and I'm going to erase off this right-hand part of the line. Same idea if I were to graph x squared. We remember that from the appendices that we've studied, that y equals x squared is that parabola centered at 0, 0 that opens up. And I only want the piece of that parabola where x is greater than 1. So I'm going to come over here to x is equal to 1 and see where I am. Well, I would be at the point 1, 1. Since it's just greater than, I'm going to put an open dot there. And the values that are greater than 1 would be over here to the right. So I'm going to keep the piece of the graph to the right, and I'm going to erase off this piece of the graph to the left. So my final graph would just be those two pieces. Now, you can graph a piecewise defined function on your calculator. It's kind of strange how you type it in. The way that you would type it in is you would do the first piece, 1 minus x, times its parameter. So you would do 1 minus x times x is less than or equal to 1. Then you do the same thing with the second piece, x squared times x is greater than 1. And then I just add those two pieces together. So this is what that would look like. I would do 1 minus x times x is less than or equal to 1, and x squared times x is greater than 1, and then I would just add those two pieces together. Now, the less than, equal to, and the greater than come from my test menu. So if you do second math, that's your test menu, that's where you would find those inequalities. And sure enough, when I graph that, you'll notice that it generates a graph that looks just like that one that we had generated by hand a second ago. I would need to trace to be able to figure out if I had open dots or closed dots and that type of thing. All right, then example 8, they asked me to sketch the graph of the absolute value function. Now, that is a graph I should know what it looks like. It was one of the 6 graphs from page 100 last year in pre-cal that we had to know, and then we went on to shift it and reflect it and do all those different types of things to it. So remember the easy way we said to remember absolute value starts with a V, and it looks like that V shape. So I already know before this begins that I basically am having a graph that's centered at, 0, 0 there and basically looks like that V shape. But let's look at how we could generate that from the absolute value equation. Now, in the textbook, they are not assuming that we did the appendices. So they go through on page 19 a very similar discussion about absolute value as what we've already had. We've already talked about that when you see an absolute value, it's always going to be a piecewise defined function. If what is inside the absolute value is greater than or equal to 0, you're going to get exactly what you started with. If what is inside the absolute value is less than 0, meaning it's negative, you're going to get the exact opposite of what you started with. So we've already redefined absolute value functions without the absolute value as piecewise. We're good with that. So now let's graph that as a piecewise and see if it generates that graph for absolute value that we know it should be. So to begin with, if I'm graphing y is equal to x, I could say that's a y-intercept of 0 and a slope of 1. So y-intercept of 0, rise 1, run 1, rise 1, run 1. That's another one of those 6 graphs from page 100 from pre-cal last year that we were also supposed to know. I am only interested in the piece of that graph that's greater than or equal to 0. So I'm going to put a closed dot at 0, and I'm going to keep the values that are greater than 0. So that means I'm keeping the right-hand side of this graph. I'm erasing off the left-hand side of this graph. All right, then I want to graph negative x. Again, that's negative x plus 0. So that would be a y-intercept of 0 and a slope of negative 1. So I could go through and say rise a positive 1, run a negative 1, or rise a negative 1 and run a positive 1. So again, starting at 0, if my slope is negative 1, I can rise that positive 1 and run the negative 1, or I can rise the negative 1 and run the positive 1. Either one, we've got the graph of that line. We're only interested in the piece of that where x is less than 0. So I'm going to have an open dot at 0, but we already know the open dot in the blue graph has gotten filled in by the closed dot in the green graph, so there's not going to be a hole in my graph. And values that are less than 0 would be on the left-hand side, so I'll keep the left-hand half of this graph, and I'll erase off the right-hand half of that graph. And so sure enough, it does generate that absolute value function that we already know. All right, example 9, back to that multiple presentation of functions. They've been giving me the equation and asking me to represent it graphically. Now they give me a graphic representation of the function and ask me to represent it algebraically with an equation. All right, so in this case, they give me the graph that you see there on page 19. Looks like this guy, and I'm supposed to come up with a function to fit that. This piece right here is a line, but it's different from the line that would generate this piece right here. So I'm going to have one equation from 0 to 1, and then I'm going to have a different equation from 1 to 2, and then of course here's a different line, so I'm going to have a different equation from 2 to infinity. So that's how I knew to come down here and define these values, where I've said, okay, the first piece is going to go from 0 to 1, and then second piece from 1 to 2, and then third piece from 2 to infinity. Now, there is a little bit of flexibility here because these are all connected pieces. There aren't any holes or gaps, so I don't really know where the open dot is and where the closed dot is when the two pieces come together. So right here, when I have x is less than or equal to 1, and then down here I have 1 is less than x, you could have the equal to down here instead of up here. Same idea with the 2, because it's connected, I could have the equal to down here and not up here. The key is you cannot have it in both places. That would be wrong. Because if I have equal to right here for 1 and equal to right here for 1, if you're trying to find f of 1, how do you know which piece to plug it into? It can't be defined as two separate, one can't have two different definitions, okay? So it'd have to be one or the other. And if I had a function that looked like this guy that we had up here, I would not have the option. Because I had an open dot for 1 on this function and a closed dot for 1 on this function, then that would designate that I would have to be equal to 1 on the green function and not equal to 1 on the blue function. Okay, but again, because our pieces were all connected, when these two pieces come together right here, I don't know which one of those is the open dot and the closed dot, so I could define it either way. So there is a little bit of flexibility there. Okay, so for this first piece, we want to come up with the equation for this little guy right here. So what would that be? Y equals what? Y equals x, right? So we've got y equals x from 0 to 1. Now, for this piece, I would probably extend it on up just so I could see where its y-intercept is. And then I could say, okay, it's got a y-intercept of positive 2, and it's got a slope of negative 1 just by counting my rise over my run. The other thing you could do is you could say it's got a point at 1, 1, and it's got a point at 2, 0, and you could create the equation of the line given 2 points if you'd rather do it that way. But to me, it just felt easier to extend this up and say it's got a y-intercept of 2, rise negative 1, run positive 1. It's got a slope of negative 1, so that would be negative 1x plus 2 or 2 minus x, however you want to write that. All right, then how about this piece? What's that equation going to be? Y equals what? 0. So there is our piecewise defined function. Now, if you're looking for a real-world application for this, over on page 20, they talk to us about example 10, about postage. Postage is a perfect example of a piecewise because the weight of your letter or your package or whatever is going to determine the shipping price, right? So let's say that your box is, I don't know what the cutoffs are, but let's say that your box is between 1 pound and 2 pounds, it's this set price. But if it's between 2 pounds and 3 pounds, it's a different price, right? And if it's between 3 and 4, it's a different price. So we could go through then and define that as a piecewise based on the weight of your box. So the cost would be dependent on the weight. The weight would be the independent variable, cost dependent variable. So I could write that as C of W, and I could set it up as a piecewise defined function based on current postage rates. If I graph that, if you look at figure 22 there on page 20, they show you what that graph would look like. And it basically just looks like little stair steps, right? That's called a step function, and that's a bold print term there on page 20. A step function is the one that literally just looks like little stair steps when you graph it. So it's definitely a piecewise defined function. An example that we saw last year about that was the greatest integer function. That was also a step function and a piecewise defined function. All right, so on page 20, they remind us of symmetry, even, odd, neither, symmetric functions. All right, so if you are trying to test a function to determine if it's even, odd, or neither, you're going to test it algebraically the exact same way every single time. You're going to put a negative x in the place of x. So I'm going to put a negative x in the place of x in my function, and if I get the exact same function that I started with, my function is even. I'm going to put a negative x in the place of x in my function, and if I get the exact opposite of what I started with, the opposite of my function, then it's odd. So I should be able to give you nothing but an equation and no means to generate the graph of that equation, so no graphing calculator or anything like that, and you determine whether it's even, odd, or neither just by testing it algebraically. So here's what I'm talking about. If in example 11 they gave me f of x is equal to x to the 5th plus x, all right? If I want to test that algebraically to see if it's even, odd, or neither, I'm going to put negative x in the place of x. So that would give me negative x to the 5th plus a negative x. If I simplify that, I get negative x to the 5th minus x. And I look at that and I think that's an odd function, like it looks like the opposite of what I started with. This is a really important practice. If you think it's an odd function, factor a negative out of it. So I'm going to go through and I'm going to factor a negative out of that, and then I'm going to have a negative of x to the 5th plus x. And then it is crystal clear to me, yes, that is a negative of the function that I started with. It is the exact opposite of the function I started with. So that means that it's an odd function. All right, look at the next one. If I wanted to test this strictly algebraically, I would put a negative x in the place of x. So that would be negative x to the 4th. So when I plug in a negative x, I get the exact same function that I started with. So what is this one? Even. All right, look at the last one. If I put a negative x in the place of x, this is why I tell you that it's a good practice that if you think it's odd, to try to factor a negative out of the function. Because at first glance, this one looks odd. If I go through and I put negative x in the place of x, negative x in the place of x, I'm going to get negative 2x minus x squared. And I look at that and go, okay, I had 2x minus x squared. This is an opposite of what I started with. But if I do that good practice of factoring out the negative to genuinely check and make sure it's the opposite of what I started with, I can see that it's really not. Because when I factor that negative out, I would have 2x plus x squared instead of 2x minus x squared. So it wouldn't trick me. So that's a really easy one to get confused and think that it's odd. It's not the opposite of what I started with, and it's not the exact same thing as what I started with, so that would be neither. All right, not only should we be able to check these algebraically, we also should be able to check these graphically. So I should be able to give you a graph with no equation associated with it at all, and you be able to tell whether it's even, odd, or neither based on the graph. So let's look at how we do that. By the definition of an even function, we said when you plug in a negative x, you get the exact same function that you started with. So when you plug in negative x, you get f of x. You just get regular y, right? So for every xy, when you plug in a negative x, you just get y. So for every xy, you have a negative xy. Look at the graph of this even function down here. Let's say that we came over here to and up to that point. If you have the point 2, 2, you should also have a point negative 2, 2. And so sure enough, if we come down here, negative 2, 2, yeah, there's a point there. That's symmetric. The easiest way to see even symmetry is it's just symmetric with respect to the y-axis. So that means that I should be able to fold this graph on the y-axis, and it should fold on top of itself. All right, for an odd function, we said you put in a negative x and you get the opposite of what you started with. So when I put in a negative x, I get a negative f of x or a negative y. So for every xy, when I plug in a negative x, I'm getting a negative y. So come down here and look at this function that we said was odd. Let's say that this is the point 1, 1 right here. Then if I have the point 1, 1, I should also have the point negative 1, negative 1. And sure enough, if I come over here, negative 1, yeah, I have a point there. The easiest way to see odd symmetry is symmetric about the origin. But those were the ones that we said, if you turn them upside down, it's the exact same picture upside down as it is right side up. That's the easiest way to see it. Okay? So let's go back to example 11. Let's say that we did not have those equations. We only had the graph to try to figure out if these were even, odd, neither. If I look at this guy, if I turn him upside down, he's the exact same picture upside down as he is right side up, so that would tell me odd. For this one, if I fold it on the y-axis, it folds on top of itself. If I turn it upside down, it's not the same thing upside down as it is right side up, so that one's even. And then for this one, if I turn it upside down, right now it's a frowny face, and if I turn it upside down, it's a smiley face, so it's definitely not the same thing upside down as it is right side up. And if I fold this on the y-axis, I'd have to have like this piece right here, I'd have to have one of those over here, and I'd have to have like this piece over here, and I'd have to have like this piece over here. I don't have any of that. So it's not symmetric with respect to the y-axis, so that would verify for me that it was a neither as well. Okay. So again, I should be able to give you an equation with no graph and you figure it out algebraically, or I should be able to give you a graph with no equation and you be able to figure it out graphically. Again, multiple representation of functions. All right, last thing that we want to look at is a definition for increasing and decreasing functions. I know that you can look at this graph and you can say, okay, it increased from negative infinity to 0, and then it decreased from 0 to infinity. I get that. Or it's going up, so it's increasing. It's going down, so it's decreasing. But the definition that they give me in the textbook is a little more confusing than that. So I wanted to go over that with you and make sure that you understood the definition that it gave you. They said a function is called increasing on an interval if y1 is less than y2 whenever x1 is less than x2 for all values in that interval, okay? It's increasing if y1 is less than y2, and that has to be true for every pair of x1 and x2 in that interval where x1 is less than x2. Okay, take any 2 points. If I had an increasing function, and I labeled this my first point and this my second point because x1 has to be less than x2, you can see absolutely this y value y1 is lower than this y value y2. So that makes sense. Y1 would have to be less than y2. But if it's a decreasing function, meaning that it's going down, again, this is x1, x2, you'll notice that y1 is higher than y2. So y1 would have to be greater than y2. So it makes sense once we see pictures associated with it. Something else to remind you of with intervals of increasing and decreasing, remember that we're looking at the x values. We didn't come up here and say this was increasing from negative infinity to positive 2. I'm not looking at the y value. The y tells me if it's going up or down, but the x value tells me where that's occurring. So it was increasing from negative infinity to 0, and it was decreasing from 0 to infinity. Also remember that we always use parentheses with those intervals. If you use brackets, when you get to 0, it can't be increasing and decreasing at the same time at 0, right? All right, so here is our homework for tonight on pages 23 to 24.